Welcome and good morning everyone. So today our lesson we continue with phytochrome. Okay, so phytochromes, okay, they are photoreceptor pigments, okay, which can be found on plants. And these phytochromes, okay, consist of blue-green pigment that promotes or inhibits growth of plants, germination, and flowering. Okay, so apparently this is how a phytochrome looks like. Okay, and you can see it has these two identical protein that has this chromophore, right? So these phytochromes apparently they are found in all plants and synthesized in leaves and seeds. Okay, and then these phytochromes exist in two photo-interreversible forms. So meaning to say, these phytochromes, okay, they exist in PR as well as in PFR form, and they can change, right, from one form to another. Depends on the type of light they are being exposed to. All right, now so let's go into detail of this on these types of phytochrome. Okay, so first one we have the PFR. Okay, or it is also known as P730. Okay, and students, when you write in the exam, this PFR, the P is a capital letter, the F and R, they are small letters, right? And if possible, they are being written, the FR, right? The FR, they are being written in a subscript, okay, subscript. So this PFR, okay, or P730 absorbs far red light. Okay, it only absorbs far red light. It does not absorb red light. It absorbs far red light. And this far red light, okay, their wavelength is 730 nanometer. So this PFR absorbs far red light maximally at 730 nanometer wavelength. And then this PFR is the active form of phytochrome. Okay, now another form of phytochrome is the PR or P660. Okay, the PR, the R is being written as a subscript. Okay, and then this PR absorbs red light, okay, or white light maximally at 660 nanometer wavelength. That's why this PR also known as P660. And this PR is the inactive form of phytochrome. Okay, you can see here in this diagram here, when this PR, okay, absorbs red light, okay, this PR will quickly, okay, converted into PFR. And when this PFR absorbs far red light, this PFR will slowly, right, or gradually converted into PR, okay, in plants. And then it depends on the type of plants as well as the concentration of this PR or PFR, which eventually will trigger the secretion or release of florigen, which in turn will trigger flowering in that particular plants. Okay, we are going into that later. This phytochrome, okay, they are synthesized in the PR form, right, to absorb red light during the day and then rapidly converted to PFR form. The PFR form, however, absorbs far red light during the night and slowly or gradually converted into the PR form. Now, let's continue with photoperiodism. Okay. Photoperiodism, okay, is a phenomenon where plants respond to changes in day length, right, relative to the dark period in a 24-hour cycle. And then there are three types of plants based on photoperiodism or photoperiodic group of plants. Okay, apparently in animals, we don't have photoperiodism, but we have biological clock or cardiac. I can't recall. They have this one terminology for that. Okay, right. But to make things simple, in plants they have photoperiodism, and we have biological clock. Right. So now let's take a look at this plant's photoperiodism. Right. So now the first type of plants, all right, or group of plants based on photoperiodism is the day neutral plants. These day neutral plants, okay, they are the plants that produce flowers independent of the dark periods, where either their dark period is shorter or exceeds than a critical night length, they will still flowering. Okay, meaning to say they will still produce phlogiston that eventually triggers flowering. These were day neutral plants. And then we have short day plants. Short day plants. Okay, this okay. Sorry, we have short day plants, and then another one is we have the long day plants. So basically, short day plants they have longer dark periods, and long day plants they um, they want to have shorter dark periods for them to flowering, right? So let me rephrase that. Short day plants they want to have longer dark periods, okay, for them to um, flowering, right, to enable them to flowering. And while the long day plants need shorter dark periods, okay, to enable them to flowering. All right, now short day plants, let's go to detail this into this. All right, short day plants, they are plants that produce flower if the length of dark period, right, or the dark period is longer than a critical night length, okay, or the length of critical dark period. Simply, we can say that these short-day plants, all right, they are plants that produce flower if, okay, their dark period is longer than a critical night length, right? So, meaning to say this short-day plants, okay, they want longer dark periods, right? They don't need much of a red light, sorry, far red light. So the short day plants needs far red light, right? Far red light, far red light, lights that can that is available during nighttime, right? So that makes sense. Short day plants, short day. They want to be exposed to the red light as minimal as possible. They want longer dark periods. So short day plants need far red lights. Okay, when these short day plants, okay, sorry, these short day plants, all right, they need far red light. Okay, and then what happens when they receive the far red light? The PFR, right, their PFR P730 will absorb the far red light. Okay, because P phytochrome, FR far red light. So PFR phytochrome that absorbs far red light. So when this PFR absorbs far red light, what happens? This PFR will gradually convert it to the PR, right? Low concentration of PFR, because most of the PFR already absorbs the far red light and converted to the PR, right? So now we have low concentration of PFR, okay, as well as high concentration of PR. Okay, let me rephrase that. When PFR already gradually converted into PR, we will have low concentration of PFR. or high concentration of PR. And these conditions will trigger florigen. Okay, and this florigen will trigger flowering in short day plants. Now, long day plants, they are plants that produce flower if the dark period, right, is shorter. It is an easier. Shorter than a critical night length. So apparently long day plants, they are the opposite of the short day plants. Long day plants, they want to have shorter dark period, okay, than a critical night length. So long day plants, they need more red lights, right? And this red light is available during the day, right? Abundantly. This red light is available abundantly during the daytime. So long day plants need more red lights. Okay, and then in this long day plants, their PR or P660 will absorb the red light. Okay, after the PR absorb the red light, the PR will rapidly converted into PFR. Okay, into PFR. And then high concentration of the PFR or low concentration of the PR will trigger florigen, right? It will trigger the synthesis of florigen, which in turn trigger flowering in long day plants. Okay, so keep in mind the presence of florigen, okay, a chemical compound in plants. The presence of this florigen will trigger flowering in the plants. So apparently plants, they need florigen for them to flowering. Okay, now as all of you have known, right, short day plants, they want longer dark periods, right? Whereas the long day plants, they want shorter dark periods, okay, than a critical night length. So now, if these plants, okay, they are exposed with flashing of red light or white light, okay, flashing of this white or red light will increase the concentration of PFR, right? Because why does the flashing of red light increase concentration of PFR? Because red light, okay, when we flash a plant with red light, the plant's PR will absorb the red light. What happens after the PR absorbs the red light? The PR will convert into PFR. Okay, so what will happen to concentration of the PFR? Increase. Betul kan? Obviously, memanglah. Okay, so flashing of red light will increase concentration of PFR. And flashing of far red light will decrease the concentration of PFR. Kan? Sebab PFR, bila dia sudah absorb itu red light, far red light, okay, PFR absorbs far red light, PFR akan jadi PR. So, concentration of PFR akan kurang, and then concentration of PR increase. Okay, concentration. Okay, now, these are the list of long day plants, short day plants, and then neutral plants. Right? Surprise! Chrysanthemums, they are short day plants, not a long day plants. Okay, they are short day plants. Okay, so these are the list. So students, for your STPM, okay, you must know some. You must be able to identify some of the plants in the short day, long day, and neutral. Right? So yang paling common, chrysanthemums, okay, dahlia, morning glory. Okay, don't be confused. Nama morning glory, morning. Macam Danish long day plants, tapi dia short day plants, similar with chrysanthemums. Right? Then rice, soya beans, tobacco. Right? while or whereas the long day plants examples are barley, cabbage, carrots, lettuce, onion, petunia, okay, poppy, radish, spinach, wheat. These are examples of long day plants. They're neutral: balsam, beans, chilies, cotton, cucumber, dandelion, okay, maize, potato, okay, and then tomato. All right, tobacco. Okay, I'm not sure why there are two tobacco here. Okay, so I think for this tobacco we ignore first, right? Or you can Google up, okay, which group this tobacco really fits into. Okay, now just now I mentioned about the flashing of red lights. Sorry, flashing of lights, right? Red lights or infrared lights, okay, on the photoperiodism. So this is it, right? These dotted lines here, okay, is the critical night length. You see, long day plants, right? Long day plants, right? They must have dark period which is shorter than the critical night length. You see, this is their dark period which is shorter than the critical night length. Whereas for short day plants, right, they are flowering when their dark period exceeds the critical night length, right? Now, flashing of red lights. Okay, what will happen to the short day or long day plants? So, a flash of red light will shorten the dark periods. Okay, by right, for the short day plants, right, you can see the dark period is exceeds the critical night length, but a flash of this red light, okay, will cause the short day plant not to flowering. Okay, whereas for the long day plants, by right they shouldn't flowering, but then they flowering, right? Now, what will happen if we, after we already flash a red light here, we flash another far red light here, as what is shown here? What will happen is the far red light will cancel off the effect of the red lights, right? So the short day plants will flowering. Why? Because their dark period exceeds the critical night length. Okay? By right, these short day plants will not flowering. Okay, but the flashing of this far red light causes them to flowering, although they have been exposed with the red lights. And you can see for the long day plants, it will not flowering because of the flashing of this far red light. Now what happens if we further flash another red light here? What will happen? Okay, this far red light already cancel off the effect of this red light. Then if we flash another red light here, this red light here will cancel the effects of this far red light. So what happened to the plants? It will go to the same effect as the initial, the first one here. So for the short day plants, it will not flowering, but the long day plants will flowering, although the dark period exceeds the critical night length, right? And then what happens if we flash another far red light here? Again, this far red light here, okay, which is shown here, will cancel off the effect of this red light, and this will cause the short day plants to flowering and non-flowering for the long day plants. Okay, so that's it for today. Okay, bye.